In mid-1905, Albert Einstein derived what is now the most famous equation in the world, E equals mc squared. But he didn't just write this down out of the blue. It followed directly from his paper on special relativity that we talked about in last week's video. And here's how he did it. Suppose you're watching a cat float freely in empty space, when suddenly it emits a flash of light in all directions. The light carries away some energy, we'll call it E, so by conservation of energy, the cat must have lost energy E. But since the light was emitted symmetrically in all directions, it won't have changed the cat's velocity. So where did the energy for the light come from? Never mind that now. Let's imagine you get bored and zoom off in a spaceship in the middle of the experiment. But from your new perspective, you're sitting still in your spaceship, and the cat is the one moving past outside the window. Therefore, you'll calculate that the cat has some kinetic energy, that is, energy of motion. And when you see the cat emit the flash of light, you'll again measure that its energy decreases by the energy of the light. Except now that you're moving, special relativity tells us that time passes at different rates for you and the cat, so you'll measure a different value for the frequency, and thus energy, of the light. This is the relativistic Doppler effect, and for our purposes, it amounts to multiplying the energy of the light by 1 plus your velocity squared divided by twice the speed of light squared. So to recap, if you take off at velocity v, you'll see the cat gain some kinetic energy ke1, then at the flash, you'll see the cat's energy decrease by e times 1 plus v squared over 2c squared. On the other hand, if you wait, you'll see the cat's energy decrease by e, and now when you take off, you'll see it gain kinetic energy ke2. But this is silly. You never touch or otherwise influence the cat in either case, so we should get the same total energy at the end. Rearranging, we see that the kinetic energies before and after the flash must be different. And the kinetic energy of an object is 1/2 of its mass times its velocity squared. But we know that the velocity was the same in both cases. So in order to account for the difference, the cat's mass must change when it emits the flash of light. Now, if we cancel things out, you can see that the change in mass of the cat must be equal to the energy of the light emitted divided by c squared. Or, as you've heard before, E equals mc squared.